Okay, today we are going to talk about the geology, hydrogeology, hydrogeochemistry, and some of the important issues in the Arabian Aquifer.
The Arabian Aquifer largely sits on one of the youngest tectonic plates on the planet, known as the Arabian Plate. This plate split off of the African plate about 25 million years ago and has continued to drift north since. The Arabian Peninsula can be split into two sections, the Arabian Shield and the Arabian Platform or Shelf. The Arabian Shield is on the western side of the peninsula closest to where the rifting started. This section of the peninsula is extremely arid with very little soil, and the shield is largely exposed. It is estimated that the shield exposes about 50% plutonic and 50% volcanic and sedimentary rocks. Some examples of these rocks are cherts, andesites, gneiss, metabasalts, and more. The Arabian Platform sits on the eastern side of the peninsula and is largely composed of sedimentary rocks with sporadic evaporites. The thickness of the sedimentary deposits varies. For example, around eastern Jordan and Syria, it is about 4 to 5 kilometers thick. Then it thickens to about 8 kilometers around the big red dot, and it continues to grow to 13 kilometers close to the Persian Gulf. All of these were deposited by multiple sea level changes over time. On this map, you can see the elevation changes as a gradual slope towards the east, which explains the variance in the thickness of the deposits. Here is a general map of the geology of the Arabian Peninsula. You can see the difference between the shield and the platform a little better just based on the rock types and the age of everything.
So the Arabian Aquifer is composed of a group of aquifers, and they're hosted in various geological formations. As you can see this diagram, they also range wildly in age. You have this Paleozoic aquifer system, and then you have Cretaceous, and then you have some that are less than 10,000 years old. Those serve as alluvial system. And they generally deeps to the east. So there are two kinds of aquifers. You have alluvial aquifers, which are 4 to 20 meters deep. They're pretty shallow. They're mainly sand, so pretty high hydraulic conductivity. They're very prone to contamination just because they're so close to the surface, and they're recharged by seasonal runoff. Then you have those sedimentary aquifers that are deeper and mostly confined. They're composed of sandstone, limestone, and dolomite. The presence of limestone and dolomite imply that you have dissolution of carbonate rock, which form karst aquifers. And a lot of the water in those aquifers actually comes from fossil water, which is just water that very old. They're from the Pleistocene when the climate was much wetter, and they're much thicker, ranging from 200 to 900 meters in thickness. And this is just a diagram showing the karst aquifer, which is the Uya aquifer, as you can see here. The karst aquifer have very high hydraulic conductivity. It's just the nature of karst, making there are many conduits and many cracks where the water can go through. In terms of hydrogeochemistry, salinity is very high in part of the aquifer because of high evaporation near the surface, and also saltwater intrusion. Iron concentration is lower in wet season, as you can see here. The top diagram shows the iron concentration in dry season, and the bottom diagram shows the iron concentration in wet season. And as you can see here, all the major ions decrease pretty significantly, although the salinity is still pretty high in this case. There's substantial amount of NO3 and SO4, which indicate there's some anthropogenic contamination going on, mainly from agricultural runoff.
So in order to address the issues of the aquifer that the region is having, they have taken steps to not rely on the aquifer as much by doing things like desalination plants, like pictured here in Al Jubail, which is in Saudi Arabia, one of the more wealthier areas. And you can see here on this geographical map diagram that shows plants along the Arabian Peninsula. So with desalination, it's just taking the seawater intrusion and removing the salt and making it safe for human consumption and drinking. So that's a big thing, but it is very costly. We also have the GRACE technology, which is a pair of satellites that are in orbit above us currently. The Gravity Recovery and Climate Experiment, there are satellites that measure the mass distribution and mass flux of Earth's water. This is really good in tracking water loss and land subsidence that occurs in the Arabian Peninsula or the Meghra Aquifer system, which it is a part of, which you can see in the GIS mapping down at the left-hand corner. Another technique that they are using is seawater reverse osmosis, or just regular reverse osmosis, which is just another way of taking brackish or seawater and making it safe for human consumption. We also have the MAR, which is a concept, the managed aquifer recharge, which improves water quality by utilizing natural contaminant attenuation processes. So things like this, it's just a way to either track, manage and monitor the aquifer already in the current loss, or ways to not rely on it as much. From the next slide that we can see, this aquifer is heavily dependent on a lot of people. It covers about 60 million people's needs. It stretches from the UAE, Oman, Kuwait, Qatar, Jordan, and Yemen. So it is vitally important that these issues are addressed regionally as well.
So the people in the Arabian Peninsula are very dependent on the Arabian Aquifer. 80% of the Arabian Peninsula retrieves their water from the Arabian Aquifer, and 50% of large cities use the groundwater from the Arabian Aquifer, as well as 80% of cultivated areas use this water to irrigate their crops. And in 1980 to 1985, within a 5-year period, they saw that there was an increase in 264% for demand in water. And in that 1980 study, by 2010, it was estimated that it was going to be a 2,000% increase. And with these numbers, it shows that the Arabian Aquifer is the most overstressed aquifer in the world. It supports more than 60 million people. So when you have this overstressed aquifer, it leads to depletion, and that when water withdrawal is greater than recharge. And this leads to decreased water levels and decrease in water yields. It could also lead to deterioration in water quality, decline in the water table, saltwater intrusion, as well as subsidence in the land from depletion in volume in the ground. And since since depletion is so high, is because there's such a little recharge. The recharge time is between November and April, and they only get around 600 millimeters a year, with facing against high evaporation rates of 3,000 millimeters a year. And these deep fossil aquifers from the Ice Age that formed, they do not recharge. They only have a set amount, a volume, and they cannot be recharged. And that the graph below it shows where a lot of shows the depletion as well as the extraction rate from these different years. So this figure shows all the aquifers around the world. The ones more in the red and the brighter colors are ones that are losing more and having higher depletion rates. And there's ones that are blue and green, which show that they are actually gaining and having more recharge in their aquifer. So the effect on farmers so there's around 30% of the population is involved with labor activities and farming life. And as depletion increases, the cost of pumping the water increases. So farmers cannot afford to grow their crops, and it leads to less crop production, which leads to increase in food prices, which means more farmers are going to abandon their farmland, which leads to desertification, urban migration to larger cities, and then just high unemployment rates, which can affect it. And then there's many more issues that happens when depletion rises. When water quality decreases, water becomes more brackish, or there's more total dissolved solids, which means the water quality decreases. There's subsidence along the entire aquifer from the northwest to the southeast. That's around 5 to 12 millimeters a year, especially in areas which are 150-meter drawdowns. And in the 1980 study, there's predicted that that the whole entire Arabian Aquifer will be depleted by 2050, and this has led to many natural springs dried up, and many areas being subsidized, and as well as areas like Riyadh, where groundwater has dropped 10 meters in the past 30 years, which is insane.